Okay, so what are we going to talk about today as it pertains to rate limiting and Redis and how we can offer value here? So first things we want to cover is why is rate limiting necessary at all? It's a very good question. I'm assuming that if you're coming to this webinar, you already have some idea of the need for rate limiting. We're going to cover a few scenarios that we've run into in production. We'd like to discuss some of the prerequisites that you will have to have an efficient rate limiting infrastructure. We'll discuss one or two of the methods around rate limiting that we've used in production. And finally, we'll cover some anti-patterns. If you have questions anytime during this webinar, please feel free to go ahead and submit them. If it's pertinent to what we're doing, we'll get to it. Otherwise, we'll push it to the end. But we do want to answer all the questions for everybody so that you get the most value from this webinar. The first question we need to go is, why do we need to rate limit at all? So say your boss comes to you or the product team comes to you and say, let's open up our API via data via API so that our customers can query their own data. As a customer, this is great news, right? You want to be able to access your own data, slice and dice it, maybe throw it through some machine learning or some analysis tools to get things that are valuable to your business, right? And as a provider of this data, this is great because then you can allow the users to do what they need to do and provide more value with less effort on your side. Now, the problem with this comes out in what's called the tragedy of the commons. And this is actually a situation from economics where that originally started from people grazing their sheep or cows in the town square on the grass. And what they found was that each person acting in their own best self-interest basically caused a depletion of the resources at scale. And so how do we manage these resources that we're providing to the customer through data in a way that is fair to all of the different clients? So here we have an example of what would be an API available open to the internet. We have two consumers, consumer one and consumer two. I use the term consumer because it could be, a web browser, or it could be another API that is consuming data from your original API. So I like the term consumer because it really, and then producer on the side of the people sending out the data because it's more clear. So these API requests would go through, say, a load balancer to a bank of API servers. Those API servers would make requests to your data store. In this case, we're using MySQL database, but it could be any data store like Cassandra, Elasticsearch, or even better, Redis on the back end, because that's the fastest data store that we know of. So consumer 2 goes ahead and submits a hot request through the API to the load balancer. That is routed to the first API server. That's translated into a database request that is very expensive. It could be something like a full table scan. It could be trying to collect huge amounts of data that need to be serialized and sent back over the wire. Once that hot request hits the data store, pretty much all hell breaks loose. And it's starting now, that is starting to slow down the requests that are coming in to other consumers. And now the consumer 2 is starting to affect the performance of consumer 1. And we get ourselves to a full-fledged dumpster fire, which is definitely where we don't want to be. How do we know all this? Well, this has happened personally to me a couple of times in my career. I can tell you about the worst case that I've ever seen. This was a large corporate client, so very large, one of the Fortune 500 or Fortune 100 companies who was pulling data from our API. And they had a very, very large infrastructure, and they didn't communicate well internally. And so what happened was that someone somewhere was making this incredibly expensive request, requesting 5 years of data every minute, and basically taking out our data store. To troubleshoot this, there are a variety of ways we could do this, but the problem was they had a single network egress point. All of their traffic was NATed out to the internet through a certain limited number of gateways. So they masked the internal IP address that was calling the API. So we didn't have any way by IP address identifying this. If you were running microservices in your own data center, you would not have this problem because you would have the IP address that is calling your API. You'd be able to log onto that machine, figure out what process is running, and narrow down the culprit. Another issue that we had was one single shared API key. Well, for every customer, we only cut one API key. And that API key was passed around amongst developers within the organization, meaning that we had no way of telling which developer group was going to try and access this data. And if we wanted to turn off this API key and disable it, we would end up disabling the whole organization that had business critical information also being pulled in. There was also a lack of interest in chasing this down. Chasing down web traffic in your own data center, you have a million other things to do, is very, very time consuming and difficult. And lastly, this was a very expensive data operation. Like I said, 5 years of data queried every minute in some script that kind of went wild. And so it was basically taking out our data store and making it very difficult for us to service other client requests. And again, this is the worst possible case that can happen in a rate limiting scenario. If we're going to set up rate limiting, there are a couple of prerequisites that we need to have in place first. So we need a fast centralized data store. Oops. We need some way to estimate the cost of each call coming in, and generally that's done by path. And we also need a way to identify the consumers in such a manner that it provides good rate limiting fodder. So the data store, you need to have a data store that is extremely fast for both reads and writes. There are tons of data stores on the market. Only one is really, really fast for both reads and writes at this scale, and has that atomic access that you need to access the values in the store. So we are going to be atomically updating counters over time. And if we have a multi-threaded system, that's going to actually turn us into race conditions where we might leak out of our buckets, and we definitely don't want that. So we need that atomic access to the store. And finally, it needs to be easy to operate, and something that we don't want to run a specialized data store if we don't have to. Most customers and most of the places that I've worked at in the past are already running Redis. So it's pretty easy to add Redis to this equation. And it meets all of the criteria. It has the atomic updates that you need. It has the speed that is critical because you don't want to slow down your path too much. So determining the cost of a call, right? The first question you want to ask, is rate limiting necessary for this path? If this path is a call that normally completes in, say, microseconds, do you really want to add on, a couple of extra milliseconds on either end to handle this fast running call that is light on resources? So you might take a look at this and say, okay, well, we don't need to really rate limit this specific endpoint. And so you would leave that off. The other thing you would look at, say, for example, they're calling API data 1 year or API data 1 day. You would want to adjust the cost of these different paths, right? The 1 year data is obviously more expensive. If somebody's querying the 1 year data every minute, they're definitely not storing that data and they're performing some weird calculation every time. You want to make sure that you make it easier for them to calculate each day, pull that down and store that. And finally, you want to assign values based on the resource consumption. So maybe the 1 year query on the API is actually really fast because it is a roll up over a year that's already cached. So in that case, you would assign it a much, much lower score, whereas the 1 day, you're obviously calculating that every time, and so maybe that's more expensive. So you need to figure out how expensive and how resource intensive all of your calls are to protect your data store and your other resources in your environment. Finally, you need to figure out some sort of way of uniquely identifying the consumer. And there are several possibilities here. You could use a cookie. You could use IP addresses or a token, right? Those could be JWT tokens, some sort of asset tokens, or query parameters or HTTP headers added. The cookied user is great if you're serving data via a browser, right? It's easy to set and read cookies. However, these can be easily bypassed by automated scrapers, and it requires a browser or a cookie store. So if you have some sort of API call, you would need to store the cookies to make sure that you're identified uniquely every time. So I generally don't recommend using a cookie, but it is something to keep in mind if it fits well for your scenario. The next option is the use of the IP address of the caller. You're going to know the IP address of the caller because it's part of the HTTP request coming into your web stack. However, it's often shared due to NAT gateways. So if you have a company with a large internal environment, they're going to NAT all outgoing requests and ensure they look like they come from a single IP address. And so it's not the most efficient way of figuring out at scale who the caller is. And with IP addresses, it's often not possible to tie that back to the consumer's organization. And we'll talk about some of the identifiers and why that's important, right? You could maybe go scrape whois data, but it's not formatted well, and you're never 100% sure of who owns what IPs at what time, especially on the cloud. The final kind of consumer ID method that is most common, I think, and seems to work most well on production is the token. So each consumer can be uniquely identified within a local system because they have a token that's a unique identifier. You can attach metadata to that token, and that becomes extremely important in the case of how you decide to bill and rate limit as a whole, and we'll talk about that a little bit later. When you do have a token, the most important thing that you need to kind of keep in mind is it needs to be as easy as possible to generate tokens by the consumer. It needs to be self-service. So the issue that we ran into with that large Fortune 100 company was because it was so onerous for them to get a token from us, they just shared the same token, right? So we need to make it as easy as possible for the customer to generate their own tokens and follow the best practices of each application would use a unique token to identify them uniquely, such that you could turn off one application or throttle one application without affecting the other. And that requires good communication to the customer to explain this, and good tools to generate tokens as easy as possible. For example, if you look at something like GitHub, they have an easy way to self-generate an access token that's easy for you to generate, easy for you to replace at any time necessary. So it's a good example of how to generate tokens for access to external systems. When in doubt, you can fall back on one another. So quite frequently, do they have a token when they make the initial connection? Nope. Then we can fall back to the IP address as the unique identifier. And here we might add a multiplier to the score. We'll discuss the scores later and how they work. But the idea is that if you fall back to an IP address, you're not uniquely identified, and therefore you might get much less frequent calls to the API. And then in the case where you do have a token, you would use that token and keep the score the same so that they would reach their actual number of API requests that you want them to have. Now that we've come up with our prerequisites, we decided what we're going to do. This is what our infrastructure would look like. We have user 1 and consumer 1 and 2 on the left. Now our API would be able to check the quotas against Redis before forwarding the database request on to our MySQL database. There are two kind of most commonly used methods of rate limiting are bucketing and sliding window. So we'll talk about bucketing first. The pluses of bucketing is it's very simple to implement, right? It's a simple string data structure in Redis, which is kind of the easiest to manage and requires very little deep Redis knowledge to go ahead. You can use time to live. So when you create your record, you can set a time to live, and that will automatically trim the data out of your Redis database such that you don't have to keep track of expiring things yourself. However, the downside to this method of rate limiting is it does cause spiky behavior. Below is an example of a test key, and you see the bucket on the end is that timestamp, and that's how we're going to generate our keys in Redis. So if we go ahead and we use bucketing at Wednesday morning, so you get 300 requests a day. So Monday you did your 300 requests, Tuesday you did your 300 requests. Now we hit Wednesday at midnight, and you slam through 300 requests in the first hour of Wednesday. Now you have 23 hours the rest of the day where you're not going to be able to get any data. So you've already allocated your use. This is really spiky behavior. And so this is kind of the downside to this bucketing method. What's the actual Redis happening under the hood here? When a request comes in, we're going to increment the count in the bucketed time. We are going to fetch that count. This is actually one command in Redis. When you increment it, it returns the new value with a higher value. And finally, we're going to set the TTL on the bucket such that it will expire out of the cache after the time bucket has passed. Here we have a simple Python example of some rate limiting code that we've actually rolled out to production for several customers. So in the first line, we're grabbing the current time in seconds. we are creating a pipeline. So pipe equals R pipeline. So when we pipeline together commands in Redis, we're eliminating the back and forth on the network between each command. If we didn't use a pipeline, we do the anchor by, we'd make the connection, anchor by, get the result. We'd make the connection, we get the result, and we make the connection expire. So that's 3 different network hops that we needed to do. Now here, because we're using the pipeline, all of these commands will be fired off serially to the Redis database. And because Redis is single-threaded and atomic, it will come back in the exact order that we sent them in. So the first call, we're saying increment by, and the API is the name of the API or the user, and then daily. So we have a daily bucket, and you can set your buckets to seconds, minutes, hours, or daily, and depending on how you decide to rate limit with your customers. And you can do a combination of both second and minute and daily. So it depends on how you want to smooth out any spikes in the calls to your API. So what we're doing is we're taking the epoch time, which is the current timestamp. We're dividing it by 86400, the number of seconds in the day, then returning it into an integer, so we lop off anything at the end, and then now we're getting a bucket time back, right? So we're all good to go. Then the next thing we do is we get that value back, and this step can actually be eliminated, and in the example code we have on GitLab, I kept it in just so that you could understand that we're fetching the data back. And finally, we're going to go ahead and set expire. And what the expire does is it sets the time to live on this key to 86401, meaning that that key will now at least stay for 1 second past a day in our cache so that we're sure that we have it if we need to go back at the end of the day. And finally, we're going ahead and we're running res pipe execute. That will return an array of the results back from these 3 commands, right? And what we're looking at is the integer that comes back exceed the number of calls per day? And if it does, we send back the response data exceeded with the status 429. In the HTTP status codes, 429 just means allocations exceeded. So it's a very common way to send back to the client, hey, you've exceeded your quota, you need to go ahead and slow down, or otherwise we'll return back the data, okay. So again, to smoothing out that spiky behavior, we would have to go ahead and do things like create a minute, hour buckets ahead of time as well, and then we'll be updating all these multiple buckets to kind of smooth out that behavior. So in that previous case where we did all 300 requests in the first hour, you might set the number of requests per hour to say 20, such that they would hit that hourly rate limit before they hit the daily rate limit, and hence smooth out some of that spiky behavior. Now the sliding window method allows us to go ahead and move the window across time so that we can go ahead and eliminate a lot of this spiky behavior. Now the downside to this is a more complex implementation. It involves using the sorted set data type in Redis. However, it is also easy to use these TTLs to trim this data as well, and it will smooth out some of the spiky behavior. So what would it look like? So say we have 300 request limit on this, right? And we're going every 10 minutes. So in the 1140 to 1150, we're only doing 280 requests. In the 1150 to midnight, we hit 310, therefore only 10 requests were rate limited, but we're doing more overall. Here, we're under the rate limit. That way that window slides along in time, and that we're constantly moving along so that we're smoothing out any spikes in requests coming in. So we're using the sorted set of daily data structure in the sliding window implementation. The key name, again, would be the API key or the unique identifier, :daily. And now we're going to go ahead and we're going to set the time in milliseconds and the route score. And that route score is what we talked about before. So that daily, that API data 1 year, the score on that might be 200. And the daily might be 100. And so instead of figuring out just the number of calls, we're going to keep score. And when the user hits a certain score, then we're going to start rating. This allows us to set different weights to different endpoints and get a much more fine-grained control of the resources that the customer is using, right? And then for the score in the sorted set, we're just going to use the time in milliseconds. And if we took a look at an example key, we'd see the Z range command, which tells us to fetch a certain range from here. And this is going to fetch them all, the test key, daily key, and -1 is to the end with scores. We'll see that there's a timestamp and a weight of 4, and then 1 and 2, and then 3 and 4. We also have a timestamp with a weight of 4. And you can see that the total score would be 8 because we would sum these up. So the kind of basic algorithm we're working with is we're going to first remove any old items for the sorted set. We're going to add the current call to the sorted set. Then we're going to fetch all of the items within the sorted set, set an expiration, and then in our application code, we're going to sum all the scores to see if they exceed the number of points that we allow to the customer for rate limiting every day. Again, we're going ahead and grabbing the current time in milliseconds instead of seconds this time. So we have more fine-grained control. We are going ahead to use the pipeline again. And remember that the pipeline will make all of our calls happen on one network round trip, save us a lot of network time. So the first step is we're going to do pipe Z rem range by score. So any command that starts with Z deals with sorted sets here. So we're going to say find everything with a score, which is the timestamp, less than the current timestamp minus 86,400. So anything that is older than a day in the sorted set, we're going to go ahead and remove. Then we're going to add our current call with the score as well, based on the route. We're going to fetch the range of everything back from that current day, because we've already gone ahead and lopped off everything from the current day, before the current day. And then we're going to set the expiration on the key such that it will expire a day from now. Then we'll go ahead and execute this pipe call, and we're going to get back. We're going to the daily score. We're going to take the sum. We're going to split that timestamp and score, and then we're going to basically sum all those up and return that for the day score. That day score has exceeded the number of calls per day allowed by the client. We'll return a 429. Again, resource allocation exceeded is the HTTP command, or HTTP status code 429, and otherwise we'll return the status 200. This all seems pretty simple, but it can get complicated really quickly. One of the interesting tips is this caller identification is the most difficult part of designing a rate limiting system, right? And there are several reasons for that. You need to just how you're going to roll up metadata you're going to provide. And then if you're all falling, so it's very common to fall back address, multiply that score by a given number, such that an unauthenticated, you get way less calls or your data API. Interesting into a lot. You token generation, you can associate meta. This becomes interesting in the rate limiting. So your customer is build kind of one sub or sub company you're dealing with. So you need to be, so your token would identify a unique user, but that would also include the billing entity, for example, that payer. And therefore, now you're going to be rate limiting based on the payer. And this becomes interesting where you're going to know the payer and you're going to see them hitting their rate limit a certain number of times a day. If you're analyzing your logs carefully, then you would go back to that consumer, that payer, and you'd say, you're reaching your limit of calls per day. You can move up to the next tier of access if that's necessary. So being able to identify by the payer is a really good way of tying that back to making good decisions about how you're going to rate limit any calls to your API. Another critical thing is to set headers with detailed information. This is very important when you're starting to troubleshoot a lot of customers that are calling with their API. They might not understand that it's rate limited. And so you want to make this as easy as possible. So generally this, if you look here, we're going to return the HTTP 1.0 429 too many requests. Pretty obvious what happened there. We get the content type and the content length. And then we're setting that X rate limiting hour remaining -1, meaning that you have no calls left for the hour, right? But you do have calls left for the day. So if you have a generous consumer who is interested about keeping track of this, they might see that request call limiting per hour to -1 and then stop making calls until that hour flips over, and then they can go back to their day calls. Right? Not necessarily the case, but if you can come back to them and point out that the headers are showing the information how much they have left, they have a good idea what's going on. Makes it a lot easier to troubleshoot and a lot easier to explain to the customer why they're getting rate limited in the first place. And finally, 429 is your friend, but I find that it's not one of the more common known HTTP return codes. So a lot of times you'll have to explain to the customer what a 429 is, what it means, and why they're being rate limited. So that's sample code that we had. There are two different links here. We have the GitHub for the rate limiting example, and the sliding window is a separate branch, and that covers it in detail. It's kind of a working example, and you can spin it up with Redis container fairly easily. And then we also have the simpler bucketing branch that goes with this as well, and that's the master. One other thing that I left out of the rate limiting tips and tricks that you need to take into consideration is the number of payers or the number of clients that you're going to have. So if you only have a small number of clients, what's going to happen is they're going to concentrate all of the activity into just one or two keys, and you may end up with a hotkey situation in your Redis database. And for that, you would need to shard out your Redis database, which is both possible with Redis open source as well as with the Redis Enterprise. So keep that in mind, that if you make the ID too narrow, that you can run into problems with resource contention, updating and reading records from your Redis database as well.
Well, thank you everybody for joining. This will be on demand. Have a great day.